Bismillahirrahmanirrahim. Assalamu alaikum students. Before going towards our examples and problems related to fluid kinematics, we are going to cover a point that we missed in the last lecture, and that is related to these two equations. You remember that this is our material derivative and this right here is our Reynolds transport theorem. So what they do is they provide a link between our Lagrangian and Eulerian flow description. You remember we talked about our flow description, that how we use these two flow description to describe our flow. If let's suppose this is our system of fluid, so if I take a single fluid particle and study its properties, so this will be represented only as a function of time. So if I'm going to see a velocity, if I want to see the velocity of this particle, so in Lagrangian flow description we'll see it only as a function of time. But in the Eulerian flow description, what we do is we define a control volume. We define a control volume. So whatever is passing through that volume, whatever flow is passing through that volume, that is what our study is about, those particles that is flowing into the volume. So what we do in this system is when we write something like this, so we will write it both as a function of position and time. So the properties in this system will be represented both as a function of position and time in Eulerian system, and in Lagrangian system it will be represented as a function of time only. So how do the material derivative and the Reynolds transport theorem provides us the link between these two systems? So if you see to the left hand side of these two equations, this is a change in certain property with respect to time, the total change, and this is the change of extensive properties of a system with respect to time. So these changes are only being studied with respect to change in time. So this is what our Lagrangian system do. Lagrangian systems gives us a change in a certain property with respect to time. And now these two equations links to this, the right hand side. If we see the right hand side of the material derivative equation, we see a change in a certain property, a partial change in time and in position. So this is the local change, this is the convective change. So we are seeing these changes both with time and position. So this is what the Eulerian description tells us, that we see a certain position, a certain property both as a function of position and time. And similarly, if we see the Reynolds transport theorem, then we can see that the first term on the right hand side gives us a change, a partial change with respect to time in of a certain extensive property inside the control volume, and is added with a change in the control surface. That control surface is our inflow and outflow surfaces. You remember this equation here, the dot product is representing the inflow and the outflow of the system, and this is what tells us about the position of a fluid going into and out of the system, and this is a change in the extensive property inside the control volume. So this is also representing the time here in the Reynolds transport theorem. This term is representing the time and this term is here representing position. So now you can see why we are saying this, that these two equations provides us a link between these two. So hope it's clear. Now let's move on to our examples. So this is our first example given. This is related to acceleration field. So the statement is an incompressible inviscid flow steadily passed a ball of radius r as shown in figure 4.4a. According to a more advanced analysis of the flow, the fluid velocity along streamline AB, this is along the streamline AB is given. So we have a velocity along the streamline. This is our velocity along the streamline. So where V0 is upstream far ahead of the sphere. So this is V0 upstream far ahead of the sphere. Determine the acceleration experienced by the fluid particle as they flow along the streamline. So what we are going to do, we are going to find the acceleration experienced by the fluid particles as they flow along the streamline. What we can derive from this statement is, one is that this is a steady flow, and this is very important. I'm going to explain it in a little while. And the next is that we are given a velocity in the x-axis only. So this is a one-dimensional fluid flow problem. This is the one-dimensional fluid flow problem. So what we are going to do, we are going to use our material derivatives, and we are then going to calculate our acceleration using our material derivative equation. So here, this is how our material derivative equation will look like. In this case, along the streamline AB, there is only one component of velocity. As you can see, that it is only this component of the velocity only along the x-axis. The next component, that is V and W, is equal to 0 because it is a one-dimensional fluid flow problem. So the y-axis and the z-axis of this velocity is equal to 0. This is how my material derivative will look like when I write it for this particular case. That is, my total change in velocity dv by dt will be equated to this acceleration, and that is my local change in velocity with respect to time, and that is my convective change. So here, this convective change in this scenario is only occurring in the x-axis because the y and the z-axis are equal to 0, as we have derived from this statement. So this is how this equation will look like, that we are going to put the u component of velocity here and the u component of velocity here. So this is how our right hand side of the equation will look like. Now simplifying it a little bit further, we are actually seeing velocity only in one axis, that is the x-axis. So we are actually computing acceleration only along the x-axis. So this acceleration will be equal to the local change, and that is the convective change. And in this case, the other two components of the acceleration will be equal to 0. So here you can now see that this convective change has been equated to 0. Why? We have derived this from our statement that the fluid flows steadily. So if you remember your previous lectures, a steady flow is the one in which if we like to see some properties, let's say a velocity or acceleration or mass flow rate, it does not change with respect to time. So here it is derived from the statement of this particular example that the flow is steady. So if the flow is steady, it is not going to change with respect to time. So all the changes of the property which are with respect to time will be equated to 0 in this case. And in this case, this was in material derivative. You know that our change with respect to time is our local change, and though that local change is this one in this case, and that will be equated to 0 because here we are looking at the partial change in velocity with respect to a partial change in time. So that is why this component of this equation will be equated to 0. This is how our final equation will look like, in which we are going to put our values. So our acceleration in the x direction will be equal to this particular term only, that is u partial u over partial x. So this is only our convective term. So here we know the value of u is given as this v0 under root 1 plus r cube over x cube. We are going to put this instead of u and the partial u over partial x, and then we are going to apply partial u or partial x on this term. So if we are going to do it a little bit more, so v naught, if you want to open this bracket and then apply the partial term, it will be more clear to you. V naught r cube divided by x cube. Okay, I have opened this bracket. So now when I am going to apply my partial u or partial x, so I will be able to only derive this term, because this is constant and these two terms are also constant. I will move x to the numerator, and this is how it's going to look like, that du or dx will be only for this x 3. So I am deriving only this x power minus 3. So this is how this term will be derived if I apply this on this terms. So this is what we are going to get if we derive it. Okay, and now going towards our final term. This is how our final term will look like, and then this was what was required to determine the acceleration experienced by fluid particle as they flow along the streamline. So now we have derived a term for acceleration along the streamline. In this case, that was along the x-axis, and now we have a term for that. So this is our final result, and if you want to plot some values and draw a graph for this, you can also do that by taking values for this term, that is for acceleration term, and plotting it against x over r, that is x along the streamline direction and r is the radius of this ball. So for different values of these two, you can plot your acceleration curve for this particular example. Hope this is clear. Moving on to the next one. So now this is a problem from your Munson book. The previous one was an example from your Munson book, and this is now a problem from your Munson book 4.53. Let's read the statement. Air flows steadily through a long pipe with a speed of u is equal to 50 plus 0.5x. So u is our x component of our velocity, where x is the distance along the pipe in feet and u is in feet per second. Here we can underline some terms from the start, which is this term. Let's come back to it later. Due to heat transfer into the pipe, the air temperature T within the pipe is this. Determine the rate of change of temperature of air particle as they flow past at x is equal to 5 feet. So what will be the change in this temperature of air particles as they move in the x direction, and in the x direction they move 5 feet. So this is the temperature field problem. We are giving a velocity field and we are required to find the temperature field. So definitely we are going to use our material derivative. That is why it is used for that. I've repeated again and again that if a velocity field is known, you can find any other property that can be temperature, pressure. In this case, this is the temperature, and we are required to find the temperature field. So we are going to use our material derivative problem here. Now we are going to put values for our temperature. So in this particular case, if we come to this term, that is airflow is steadily moving through a long pipe with the speed of this. So this is a steady flow. So again, all the terms that are incorporating the change with respect to time will be equated to 0, because again it is a steady flow problem. So the rate of change of this particular parameter with respect to time will be equated to 0. Now we are having these terms only, that is u, v, w. The x, y, z components of the velocity and the change in the temperature along these axes. So here we have only the u component of the velocity, and we are only required to see the change in temperature along this particular x-axis only. So these two terms, that is v and w, can also be equated to 0. So if we would like to write it, so here u is equal to 50 plus 0.5x. Here v is equal to 0 and w is equal to, w is also equal to 0. So now let's write the same for our temperature. Here temperature is 300 plus 10x. So now we can simplify this equation, and by simplifying I mean taking these two terms also equal to 0. So now my total change is dt over dt. Total change in time, total change in temperature with respect to time is only equal to this term u partial t over partial x. So here u is this one, here u is this, so I am going to put the value of u. U is 50 plus 0.5x, and what will be partial t over partial x. So if we are going to apply partial t over partial x on this equation, so in this case this is a constant that will be equated to 0, and we will only get this term, and applying partial t over partial x over this will give us 10 only. So we are going to write 10 instead of this term. So here it is 10. So we are going to get what? 500 plus 5x, and that will be degree Fahrenheit per second. So here, what was the value of x? We were required to see the rate of change of the temperature of air particle as they flow past the section at x is equal to 5 feet. So here we are going to put x is equal to 5 feet and see the total change with respect to time. So 500 plus 5 into 5, equating this will give us the answer 525 degree Fahrenheit per second. So this is our answer for this problem. Hope this is clear. Moving forward, again, the temperature distribution in a fluid is given by this, where x and y are horizontal and vertical coordinates in meters, and T is in degree centigrades. Determine the time rate of change of a fluid particle traveling horizontally with u is equal to 20 meter per second and v is equal to 0. There is a second part in which it is moving vertically with u is equal to 0 and v is equal to 20 meter per second. I am not going to solve this problem, but this is the same problem as we did the previous one. So you can use the previous method that we used for the previous problem. You are going to use this equation, and there are two parts, so some of these terms will be equated to 0. You can take this problem as a steady state problem. So I have told you that if it is a steady state problem, which term are you going to neglect in this equation? And in part A, you are giving a velocity only in the x-axis, in which v-axis is 0, and here in part B, the vertical, when the flow is vertical, the u component is 0 and the v component of the velocity is 20 meter per second. So there are two parts you are required to solve with for both of them, and here the temperature is given in t of x and 10x plus 5y. So it is a two-dimensional flow problem, because here we are dealing with two dimensions, that is x and y. So same method can be applied as you saw in the previous problem, and let's see if you can solve this. Please solve this and we will discuss it in our session that we are going to have this week. So moving on. Okay, so now we are going to do some Reynolds transport theorem problems, and for that we are going to take a scenario in which we have a pipe with one inlet and two outlets. So let's start assigning some values and directions to this. So this is our inlet and these two are outlets. So at inlet our diameter is, okay, I'm going to name them, that is 3, that is 2, and that is 1. These are my control surfaces, that is control surface 3, control surface 1, control surface 2. Remember, the inflow and outflow portions are known as control surfaces in the Reynolds transport theorem. So here our diameter 3 is 0.1 meter. Here our values are d1 for control surface 1 is 0.07 meter, and my velocity v1 is 2 meter per second. Here d2 is 0.03 meter and v2 is 1 meter per second. And here we are required to find our velocity at control surface 3. So we are going to apply our Reynolds transport theorem, and let's clarify some things along the way. So this is our Reynolds transport theorem in which we are going to see a change in the extensive property for the system, that is my left hand side, and equate it to the change in the extensive properties of that system inside the control volume, and also see how that extensive property behaves when it goes in and out of this system. So here, what is our extensive property in this case? As you can see, we are dealing with a mass flow rate problem. We are going to end up with continuity equations at the end if we want to find this velocity. So we are dealing with mass. So here our extensive property is mass, and what we are going to do is to apply the mass flow rate equation at the end to find this velocity v3. So how are we going to do this? So in this case, our extensive property is mass, and the intensive property will be equal to 1, because we know that b is equal to b over m, that is our extensive property per unit mass gives us our intensive property. So this is what we can derive from this situation, because it's a mass flow rate problem and a conservation of mass problem, because the total mass inside this system, let's say if it is a liquid flowing into this system like this, the total mass inside the system will remain conserved. So it is a conservation of mass problem. Because the control volume is rigid, it's not going to change its shape. If you are curious, this is our control volume, this whole shape. It is rigid, so inside this control volume the mass is going to be conserved. So it is our conservation of mass problem. So now we are going to simplify this equation for this scenario. I'm going to write it such that the extensive property, the mass inside this system, is conserved. So this term will be equated to 0, because this is what my extensive property is. It is a conservation of mass problem. So this mass inside this system will not change if we are talking about this particular control volume. Then what will happen inside the control volume if we want to see the extensive property, the change in this extensive property with respect to time inside this control volume? So again, it's not going to change. It is again the conservation of mass problem. So this particular term will also be neglected and will be equated to 0. So what we get is our equation in terms of our control surfaces, that is 0 is equal to control surface into rho b v for velocity, n is our direction unit normal, and dA. So this is what we are left with, and this is what we are going to apply this term on these three control surfaces and get an equation. So let's do this. Let's apply this term on these three control surfaces, control surface 1, 2, 3, and get an equation and then simplify it further. So let's write it as 0 is equal to integral for control surface 1. I'm going to write separate terms for control surfaces, that is my density, velocity v1, unit vector normal n, and dA, plus integral control surface 2, density, velocity at point 2, control surface 2, unit vector normal, and dA, plus for control surface 3, my density, velocity, and unit vector normal, dA. So this is how my governing equation for this scenario will look like. This is I'm talking about a liquid here. Here inside this control volume is a liquid, so its density will remain the same, so we can neglect these terms, these density terms, from my equation. So I will leave these terms out, and now I'm going to write another equation with the help of which I'm going to solve this problem. So let's move forward. Here again I have I'm left with velocity and unit vector and dA, and similar terms for control surface 2 and control surface 3. So this is my n unit vector, and n unit vector, its magnitude is equal to 1, so this will be equal to 1. These terms, this n unit vector will be equated to 1. So if I take the integral, so velocity is constant, velocity is not changing. For control surface 1, control surface 2 has its own velocity, control surface 3 has its own velocity. The only thing that is in terms of dA is my area, and I'm going to integrate this. So for control surface 1, 2, 3, so I'm going to get a final equation like this, that 0 is equal to v1 a1 plus v2 a2 plus v3 a3. So this is what my final equation will look like. Now remember, I'm going to put some signs for a fluid that is going into the system and for fluid going out of the system. As you remember, like we derived the Reynolds transport theorem, we put a negative sign for the fluid that is going into the system, and we discussed that in detail, that why we are putting a negative sign here. So please go through your previous lecture if you are not clear about this negative sign. And the fluid going out of this system will be denoted by positive signs. So this is now our final equation, and now we can solve this problem by putting values, just putting values, because we have one equation and one unknown. We have only one unknown, that is this v3. So sorry, I've made a mistake. This is the fluid going out of the system, going inside the system. So the negative sign will be put here. These two will be positive because they are going out of the system. So this is my for control surface in which the fluid is going inside. So this is how I will put my negative sign here. So this is my final equation, and we have one unknown, that is v3, and one equation. So we can now solve this equation. My area will be pi by 4. Area will be pi by 4 d square because we are dealing with pipes, cylindrical pipes. So this is what my area will be, and I have V1, I know my V1, V2, and I can compute the areas from these diameters, so no problem. And at the end I'm going to compute it for V3. So please do that yourself. This was our first problem related to Reynolds transport theorem, and if I want to go it and repeat it for you, that is conservation of mass problem, because inside this control volume the mass will remain the same, and for that purpose we have initially neglected these two terms, because the total mass within the system will remain the same with respect to time, and the total mass inside the control volume will remain the same with respect to time. So we have neglected these two terms initially, and now we are dealing with control surfaces, only those surfaces that are responsible for the system going inside and outside this control volume. So we applied this integral on this value, in which b was also equated to 1, because we were dealing with a conservation of mass problem. So b was equal to b over m, and b was equal to m, so we got a unity. So this term was neglected. Density was constant, so it was removed from this equation. We had our velocity, we had our n unit normal vector, so that is also equal to 1, and our area dA, which we computed, which we integrated and then gave it a value of this. So I hope this is clear. Let's move forward. So here we have another problem of where our extensor property is again mass, but here our control volume is the extensor property, that is our mass will change inside the control volume. So our control volume term in the Reynolds transport theorem will not be equated to 0 now. It will be considered in the equation. So let's go through the statement. It tells us that kerosene flows into 4 feet diameter cylinder. So it's a cylindrical tank through pipes A and B at 3 feet per second and 2 feet per second respectively. It exit at C at a constant rate of 1 feet per second. Determine the time required to fill the tank if y is equal to 0 when t is equal to 0. So what it tells us is that how much time will it take to fill the tank. So if y is equal to 0 means that the tank is empty at this level. Y is equal to 0 means that the tank is empty at t is equal to 0. So how much time will it take to fill the tank up to 6 feet? So this is our Reynolds transport theorem problem, and this is our Reynolds transport theorem. So here again our extensor property B is again our mass, and our intensor property will be equal to 1. So the mass of the system, that is the kerosene oil in this case, is not going to change in this scenario. So the total change in the system, that is the total change in the mass with respect to time. This is what it's telling us, the total change in mass. So there will be no change in mass. Okay, so this term again will be neglected when we go forward. So this term will be equated to 0 because there is no change in mass. Now let's come to this term, the change in mass inside the control volume. So if we take the inside of this tank, our control volume, so here we can say that the mass is now changing, because what we are required to do is to determine the time required to fill the tank if y is equal to 0, t is equal to 0. So the fluid is entering the tank and it is also moving out. So here the mass is not fixed, so the mass inside this control volume will change. So this term will not be equal to 0 in this case. And again our some of the mass is flowing in, some of the mass is flowing out. So we have three control surfaces A, B and C, so these terms will be included accordingly. So overall our total change of mass inside of the system, that is our kerosene oil, will not change, but its mass inside the control volume is changing with time. So we are not going to neglect this term, and we are going to include our control surfaces as well. So this is our initial, our assumptions which we made based on the data given. So now let's write this equation. If we are ignoring this term, so it can be written as partial or partial T, then integral control volume and density of kerosene in this case, and then our intensive property is B, which is equal to 1. So I am going to ignore it from the start and put it 1 here, and then my volume dV plus the integral for the control surface, our density for kerosene oil, and again B is equal to 1, so I'm just going to ignore it. V dot dA, I'm just going to write dA because n is unit vector normal whose magnitude is 1, so I'm directly going to write dA, which all is equal to 0. So this is now my governing equation for this scenario. So I'm going to proceed, and I'm going to neglect some other terms. I'm going to cancel them out. This is my density of kerosene. I can just move it out of the integral because it will be constant, and if we divide both sides by this term, so we can neglect this term also. So now my equation will look like this. I'm going to write it like this: partial or partial T, that is my integral for the control volume, and my full derivative for volume plus integral for my control surface and velocity and dot product with area dA is equal to 0. So after further simplifying this equation, we are left with these terms. So again, let's further simplify it, and we will get, from this integral we will get volume, and from this integral our velocity will move out because it is a constant, and we will integrate this area, so we will get area. And I am going to write in this equation this VA term for all the control, all of our three control surfaces, that is A, B and C. So at A and B fluid is going in, and at C fluid is going out. So I am going to write negative and positive signs accordingly. So here again, from this integral I will get volume, so this volume is going to go there, partial over partial T minus VA velocity at control surface A and area at control surface A minus VB velocity at control surface B and area at control surface B plus velocity at control surface C and area at control surface C is all equal to 0. So now I can solve these terms for dV by dt because I know all these values. And I can solve this equation for partial V over partial T, that is the partial change in volume with change in time. So what I'm going to do, one thing is to, when I take the area of these pipes, that area formula will be pi by 4 d square. So when I'm going to take the diameter, diameters are given here, 4 inches, 8 inches, 12 inches. So when I'm going to put the respective diameters in each value. So I am going to convert it in feet. So for that purpose I am going to divide these diameters by 12 to convert them into feet. So this is how my value for the area will look like. Let's slide it a more clean. That will be pi by 4 d square. So that will be d by 2 square. So this is how I'm going to take my area by converting the diameter into feet, because we are talking in feet per second. So for dimensional homogeneity, I'm going to do this step first before solving this equation for dv partial v over partial t. So by solving this equation for partial v over partial t, what I am going to get is a value that is partial change in volume with partial change in time is equal to 0.1745 cubic feet per second. So this is what I'm going to get now. This is my value. I will come back to it a little bit later, and some space, leave some space. Now if I want to calculate the volume of my cylindrical tank, so what will be it? What will the volume be? So the volume will be area into height. That is, if I take the area of this cylindrical tank and multiply it with the height of the total, multiply it with the height, in this case that is y, that is the liquid, that is the height of this kerosene fluid that is risen in this cylindrical tank. So what I am going to do is to write a formula for my volume in terms of pi by 4 d square. So this is my area into the height y. So now I'm getting an equation for my volume, and this d will be this value, the 4 feet diameter of my cylindrical tank. So if I put this value in this d, so what I get is my volume for this cylindrical tank for a specific height. Y is 4 pi and y. So what I am going to do is to take a derivative with respect to time of both sides. So I am going to derivate this volume with respect to time and this value of y with respect to time, and from that I am going to calculate my time. So let's do it here. Let's do it in this space. So what I am going to do is I am going to take it as dv by dt is equal to 4 pi dy by dt. Okay, I can write it like this. So I know the value of my dv by dt, that is this value. I can put it here, and that is 0.1745 is equal to 4 pi dy by dt. Okay, so now I'm going to write it here. This I'm going to integrate it for some values by cross multiplying this value by dt, that is 4 pi dy is equal to 0.1745 dt. Okay, so I'm going to integrate this on both sides for integrate this term from 0 to 6 feet, that is my total height of this cylindrical tank, and I'm going to integrate this term, this time t, from 0 to t, because I want my time t, so I'm going to integrate this dt from 0 to t. So by solving this, let's write it a little more clearly so that you can comprehend it easily. So that is 4 pi dy is equal to 0.1745 dt. So now integrate this from 0 to 6 and integrate this from 0 to t. So what we get is on this term, that is 6 is equal to 0.01389 t. So by solving this equation, we came out to see that our time t is equal to 432.5 seconds. 432.5 seconds. So this is the final answer and what was required. So what we did actually is we now took a problem in which the extensive property inside the control volume was changing. So this term was not neglected and was incorporated in this problem, and so was this term, that what we have been doing in the previous problem also for the control surfaces. Then what we did was again our extensive property in this case was mass. So we saw that the mass for the whole system will remain the same. It is conservation of mass problem, but within the control volume that mass is changing with time. So this term will not be equated to 0 and this term will be equated to 0. And then again the density will be the same for this equation. So density can be neglected, this intensive property B can be neglected, this unit vector normal n can be neglected, and at the end we get these equations. So by integrating it for dV and dA, we get an equation like this, and then writing the equation for our control surfaces, we get these equations. By solving it, we get our value for dV by dt, that is this one. Then I take my volume for an unknown height of this cylindrical tank, and by doing so I multiply the area with an unknown height y. So I get my volume like this. Then I take the derivative of this volume with respect to time, and I take the derivative of this length with respect to time. Okay, so what I get are these terms, and I know the value of this term from here, and I put the value here, and then I get these terms here, and I cross multiply it by dt, and I integrate these terms, the length y from 0 to 6, I integrate it from 0 to 6 feet, and I integrate the time dt from 0 to t. So I get an equation of this, 6 is equal to 0.01389 t, and from here I can calculate my value for time in seconds, and here if I wanted to write the answer more clearly, so t is equal to 432.5 seconds. So hope this is clear. Let's move forward. and give you some work to do yourself. Here you can see a problem in which fluid is going in and fluid is going out from a single pipe and going in two pipes. So you are supposed to apply Reynolds transport theorem, and what we are going to do is determine the required diameter of pipe at C. You are going to find this diameter by applying Reynolds transport theorem to this situation. Here I can give you some assumptions that the mass is our extensive property again here, so B will be equal to 1 and mass is conserved, so dt over dt will be 0. The control volume term partial over partial t will be equated to 0 because this mass will not change inside the control volume with respect to time, so this term will also be equated to 0. So what you will be left with is the equation for the control surfaces. So you have to write equation for these control surfaces and then solve it for this diameter to find it. So solve this and be wary of these diameters because they are given in millimeters, so you have to convert them into meter first to solve your problem so that you might get an accurate result with accurate units. And this is your assignment. You have to take a photograph of a situation in which a fluid is flowing. You can take any example by sitting just inside your homes, and you can find plenty of examples in which fluid is going in and out. If you want to study your geyser, that is your boiler, there also if you want to simply get your tap, that can also be done here. So take a simple example from your daily life and take its photograph, draw its free body diagram, mention which one is the control volume in that free body diagram, and write a brief paragraph so that I can see what you are doing, and then apply Reynolds transport theorem on that scenario and come up with something. So do it. This is an assignment and it is a graded assignment, so please don't copy it. It's simple. You can assume values if you cannot calculate. For example, if you want velocity values, you can assume that. If you want values, if you're seeing a pipe, so you can just approximately put any value for that diameter of that pipe. So where assumption is needed, you can assume values, but overall take a scenario, assume some values and apply Reynolds transport theorem on that particular scenario, or come up with a value, find a flow rate or find a diameter of the pipe or find velocity at some point. So I'm keeping it very flexible so that you guys can take any scenario, and please do not copy. Please do not copy. If I got two similar assignments, I will equate them to 0. So please don't do this. Take a simple scenario and just apply what you have learned so far. I'm also going to share a YouTube video which is very interesting, in which the extensive property is a momentum, mv. So in that case you have your total change will not be equal to 0. So in the extensive property, so go through it and see you next week and in the discussion sessions. So take care. Allah Hafiz.